All right, let's go over some examples of finding general antiderivatives. So what we're looking for each of these is we're looking for a function whose derivative is f, the one that's given. So we're looking for a function whose derivative gives us this, right? And then we're going to take that and write plus c on the end, and that's it. Now, we're going to learn a bunch of rules for doing this. We learned a whole bunch of differentiation rules in Chapter 3, and in this chapter, in Chapter 5, we're going to learn a bunch of anti-differentiation rules, which we'll actually end up calling integration rules, but we're getting there. We will learn rules, but for now, I want to start doing some examples without knowing any rules at all, because this is a very intuitive idea. Now that you understand differentiation and you've learned how to do a bunch of differentiation things, you can just like sort of figure out what an antiderivative might be, especially for something like a polynomial on number 1 here. So what we need to do is just figure out what function is going to give us this derivative, and if this is the derivative and it's a polynomial, you can pretty much expect that its antiderivative would also be a polynomial, right? That's what we've seen. Derivatives of polynomials give us more polynomials, right? So take a second to pause the video and try to figure out, just for yourself, see if you can figure out what the antiderivative of this would be, or an antiderivative, the simplest one you can figure out, and then throw a plus c at the end. So basically we need to, I'm going to explain it now. Okay, so pause the video and try it yourself, but now I'm going to explain it. We need to basically do the power rule in reverse. So let's see, capital F of x equals what? This first term has an x squared. Remember that in the power rule, you multiply by the power and then you reduce it by 1. That's what you do to take a derivative. So to undo that, to do an antiderivative, we're going to need to bump the power up, right? If we brought it down for the derivative, we need to push it up for the antiderivative. So this is the first term's antiderivative is going to be x cubed, some multiple of x cubed. Okay, so now let's think back again. To do the derivative, we were going to multiply by 3 and then reduce it by 1, right? And we can see the result of that process is 6, right? So it couldn't have been a 6 here, because then when we multiply by 3, it would have given us 18. No, we need to have a 2 here, so that when you take the derivative and multiply by 3, you get the 6. All right, so you see how this is just undoing what we were doing before, right? So now this term, 2x cubed, its derivative is 6x squared. Hey, great. So we got the first term. Let's do the second term, right? And we know we can do this term by term because differentiation distributes over like addition and subtraction. You do differentiation term by term, so therefore you must do anti-differentiation term by term as well. So now for the second term, it's going to be minus because this is minus. And then what's this going to be? What has a derivative of 2x? Well, I went over this in the first example. That would be x squared, right? And I don't want any coefficient there. I don't want any constant multiple, just times 1, right? Because I'm going to get the 2 from the power rule. There we go. Now the last term here, the derivative, if it has a derivative of 5, well, it must be like 5x, right? That's what we've seen, is the derivative of a linear term like that gives us just its coefficient as a constant. So there we go. You can double check it, all right? You can double check the derivative of this is equal to the lowercase f. And now what we want to do is just take this and write plus c on the end for the general antiderivative, right? That indicates that there could be any constant added on the end, and it's still an antiderivative because when you differentiate the constant, you just get plus 0. Okay, so there's the first one. Second one, f of x equals e to the x. Pause the video and see if you can figure that one out. All right, so I'm going to assume that you've tried that on your own. Now, this is pretty easy because we know the derivative of e to the x is itself, right? So here is itself, so its antiderivative is also itself, right? Does that make sense? Like if taking a derivative doesn't do anything, then taking an antiderivative also shouldn't do anything, right? Except possibly introduce this arbitrary constant added on the end, which we wouldn't have known. We have no way of knowing if there's a constant there or not because it's going to disappear when you do a derivative. So there's our antiderivative for that one. And then the last one here is sine of x. Again, pause and see if you can figure that out for yourself. All right, what's our most general antiderivative for sine of x? Well, we want something whose derivative is sine, right? Well, the derivative of sine is cosine, and the derivative of cosine is negative sine. So that's almost it, right? So is the answer cosine? Well, the derivative of cosine would be negative sine. So maybe what we should do is just throw a negative on there, right? If we put a negative here, then the derivative of the cosine would be negative sine, but multiply by that -1, and you're going to get positive sine again. Turns out this idea of multiplying and like that constant multiple rule where the constant multiple sticks around, that still works for antiderivatives. You can almost reason that it has to. If it works for derivatives, it has to work for antiderivatives as well. So what we want here is not cosine, but negative cosine of x, and then as always, plus c. So here are just a few examples of antiderivatives, and we're figuring these out just by using common sense and reasoning based with what we know about derivatives already. Okay, so later I'll show you how to do these a little more analytically, sort of more rigorously using some anti-differentiation rules. But first, we've got to introduce some notation for this. Okay, so I'm going to introduce an idea called an indefinite integral. Indefinite integral. Later we're going to have definite integrals. Okay, so both of those are things we're going to learn about. But we're starting with what's called an indefinite integral. This is basically operator notation for antiderivatives. And what's operator notation? Well, remember, let me pull up the very first page here. Nope, not that one. Yeah, here. Remember this notation? This capital D subscript x here means like do the derivative of whatever comes inside the brackets over here, right? Do the derivative of this stuff. That's operator notation. It's a way of writing down that we should perform this derivative operation to the following function. And that we have so far I haven't been using that because I haven't introduced it. But this is the operator notation. It looks like this. There's this big S, big sort of like tall, skinny S that kind of takes up two lines. And then in the middle here we have our function name, which you can just put f or whatever function you want. You can stick it in there. And then at the end you put a dx. And this is called an integral sign. So that big S there is the integral sign. Oh, this pen is not very good. I'll do my best. Okay, that's the integral sign. And the dx over at the end here, this is a differential. Okay, so we learned about differentials right at the end of the last chapter. Dx is a differential, and x there identifies what's called the variable of integration. Okay, so essentially when you put a capital D subscript x, that's the variable of differentiation. It's the variable that you're differentiating with respect to. But here, that's x is the variable you're integrating with respect to. And then in the middle here, you have the function, okay? And the integral sign and the dx differential at the end, they work kind of like parentheses. They're just sort of like the bookends. You put the one at the beginning and the one at the end, and then what's in between is what you want to take an antiderivative of. And that thing that you're taking an antiderivative of is called the integrand. So all this vocabulary comes from the word integral. And integral is in some ways synonymous with antiderivative. So doing an integral is like doing an antiderivative, finding the general antiderivative for the integrand. All right? Now, the termination integral, that vocabulary, really comes from that idea of area under a curve, which we're going to establish later. But so for now, I just want you to take this on faith, kind of take it for granted that this is the notation. We're going to use it to mean find an antiderivative, but then I'll explain why it is what it is later on. So up here, we could have written each of these things down in a slightly different way. We could have written that the integral of 6x squared minus 2x plus 5, and then dx. So in other words, with respect to x, that equals our 2x cubed minus x squared plus 5x plus c. Okay, so that's the notation written out with the integral. The second one, we could have written integral of e to the x, dx, equals e to the x plus c, like that. So that's how you use this thing.